All right, momentum in two dimensions. Very simply, since momentum is a vector and momentum has to be conserved, if the momentum in one direction is conserved, or if the momentum in each direction must be conserved separately, right? So if I have to conserve the total momentum, that means that I can think of it as the momentum in x has to be equal to the momentum in x, and the momentum in y has to be equal to the final momentum in y. So since momentum's a vector, we can treat momentum conservation in each direction separately, and it still needs to be conserved. We don't have to do that. We could do an overall diagram where we look at, the overall vector sum of momentum to show that it is conserved, but dealing with it in each direction is what we're going to approach in this video. So here's our little problem. Miss Revel and Mr. McClure are applying on a rolling office chair. They are both on the chair traveling at 4.2 meters per second north when Miss Revel jumps off traveling at 2.5 meters per second east. If Miss Revel has a mass of 35 kilograms, McClure has a mass of 40 kilograms, and the chair has a mass of 10 kilograms, determine the final velocity of the chair, keeping in mind that McClure is still in the chair. So, in the initial situation, we have one large object of Revel, McClure, in the chair, which is 35, 40, and 10 respectively. So 35 plus 40 is 70, plus 10 is 85 kilograms total. 85 kilograms. Traveling at 4.2 meters per second north. In the final situation, we have two objects. We have Revel, who's traveling at 35 kilograms, or is 35 kilograms, and traveling at 2.5 meters per second east. And we have the McClure chair combo, which is at 50 kilograms, and is still going to be going north, but now it's also going to be going a little bit west to compensate for this movement east. So we don't know either of these values. So starting in the north direction, we can conserve momentum. P1n is going to have to equal to P2n. In the initial situation, we have a mass total times a velocity total. And in the final situation, we have a mass chair times a velocity final for the chair, plus a mass Revel times a velocity final for Revel, as the two objects split up. 85 times an initial speed given of kilograms times an initial speed of 4.2 meters per second. And the chair McClure combo has a mass of 50 kilograms and a final velocity that we don't know. That's what we're looking for. Plus, if she's going purely east here, in the north-south direction, velocity is 0. What the heck just happened there? Oh, there we go. Velocity is 0. And so, this whole term is 0, because she's moving straight east, so she's not going north or south. All right, 85 times 4.2, 357 kilogram meter per second squared, or meters per second. 50 kilograms, velocity of the final of the chair. .14 meters per second. So, in the final situation in the north direction, the chair is going 7.14 meters per second. Now we have to do the same thing in the east direction. I'm going to do it way over here. In the initial state, or the initial momentum in the east direction, neither object is moving, so we get an initial momentum of 0. They're both going straight north, so neither are going east and south. In the final situation, the mass of the chair and the final velocity of the chair plus the mass of Revel times the final velocity of Revel. So we got 50 kilograms V2C plus 35, that's what we don't know, that's what we're looking for. 35 kilograms times a speed of 2.5 meters per second. So 0 is equal to 50 kilograms V2C, and I just punched that out. It's 87.5 kilogram meters per second. Now I'm going to move the 87.5 over to the other side. Dividing both sides by 50 kilograms. I get a final velocity for McClure and the chair to be 1.75 meters per second, negative. Keep in mind I've treated east as my positive direction, so this negative means west. So to get my overall final velocity for the chair, I got to go 7.14 north and 1.75 west. My resultant then is 7.35 meters per second north, 13.8 degrees to the west. So, by conserving momentum in each direction separately, we can get the final velocity components for each direction separately, and then we can recombine to find the overall final velocity.